Okay, 9-5, conservation of linear momentum, kind of a big deal. So we saw this a little bit in lab, but now we're getting to see it more completely, that if we have an impulse of 0, that's a little bit of a new concept, but impulse we saw last section, if there is no net external force acting on it, then the momentum of the system, capital P, is a constant. This is if it's a closed, isolated system, which is another way of saying that the final momentum of the system has to be equal to the initial momentum of the system. These are the overall system variables here. So in formal language, if no net external force acts on a system of particles, the total linear momentum P of the system cannot change. This is the law of the conservation of linear momentum. And the way you can know if you should apply it or not is check the components of the net external force. If the component of a net external force in a closed system is 0 along an axis, it could just be along the x-axis or only along the y-axis, then the component of the linear momentum of the system along that axis cannot change. It has to stay constant. It's a conserved quantity, which is something in physics we care quite a bit about. So a couple of notes here. Oops, too far. There we go. Internal forces can change the momentum of parts of the system. It can't change the linear momentum of the entire system. This is well demonstrated with Newton's cradle, which you can see here with some nice balls that actually light up. Where if you just follow an individual ball, that ball's momentum is definitely changing. But for the overall system of all 5 balls, that stays the same. They're all continuing to move side to side depending on how much you pull. If you pull 1 back, then it's always 1 moving side to side. If you pull 2 back, it'll be 2 moving side to side, which is pretty cool. Another note that you got to see in lab a bit is you don't want to confuse momentum and energy. They're very similar in the calculations, but energy is not always conserved. And for most collisions, momentum is. So note that those are indeed separate. Okay, so we have a checkpoint. An initially stationary device lying on a frictionless floor explodes into 2 pieces, which then slide across the floor, one of them in the positive x direction. What is the sum of the momentum of the 2 pieces after the explosion? Can the second piece move at an angle to the x-axis? See, what is the direction of the momentum of the second piece? So I want you to think about this, write down your answer even. Like really commit to one answer for each of these parts. I'm going to give you a moment to think, so go ahead and pause now. All right, assuming you paused, we can check results for part A, B, and C. So the sum of the momentum of the 2 pieces after the explosion is 0, even though they're moving, right? Even though the fact is, though, that they start out at rest with no momentum, and when it explodes, that's a lot of internal forces, but no net external force acting to push the pieces apart. The second piece cannot move at an angle to the x-axis. This is something that students often wrestle with a lot. And that's, hey, if one piece is going in purely the positive x direction, then the other has to go in purely the negative x direction. If it went in, you know, some angle relative to the positive x-axis, then yeah, the other one would have some angle other than being purely along the horizontal axis. And the direction of the second piece must be in that negative x direction. So this is a pretty quick application of the conservation of linear momentum. We'll see how it can apply to some different scenarios in the following sections. So stay tuned.